Hey guys, welcome back to another video. Today, I will be taking another one of my articles that I wrote in 2015 and I will be turning it into a video article. The name of this article is called Dark Matter vs. Dark Energy. I'm turning this article into a flashback video article. What that means is that this article was written before I came to the conclusions and realizations that I have now come to. So if you haven't watched any of my earlier videos, I definitely recommend you check out my playlist called The Majestic Crystal Universe, and I recommend that you have watched some of my earlier videos in the playlist. Some of the videos I recommend that you have already watched are What is Quantum Gravity? And I recommend that you have watched my video series called Mass, Matter, Function, Interaction of Momentum, a 5-part video series. Check those videos out after this one if you haven't already watched them. With that said, this particular video does not require that you have watched my earlier videos, but I will splice in at the beginning of this video the 1-minute video that I made that I call The True Definition of Gravity, and I will include about 2 minutes of my video, What is Dark Energy? Here are a couple clips from other sources on dark matter and dark energy, so you understand what dark matter and dark energy are, at least from quote-unquote mainstream science's point of view, so that we are on the same page.
Of all the spectacles mankind has viewed through a telescope, there are few lovelier than a spiral galaxy. Majestic whirlpools of stars, they rotate in a stately and predictable dance. The fact that we see many billions of them in our telescopes tells us they are both common and stable. It is perhaps surprising that it is relatively easy to understand the inner workings of these cosmic pinwheels. By combining physical principles worked out by Sir Isaac Newton in the late 17th century with the observed amount of mass in a galaxy, scientists can calculate the rates at which these galaxies rotate. Using these techniques, astronomers predict how fast stars at different distances from the center of the galaxy should move. Stars very close to the center move slowly. That's because there is very little mass between them and the center of the galaxy to pull them along. Stars a bit further away move faster, as they're being pulled by all of the stars in between them and the center. As we get really far away, the stars are predicted to move slowly again. Their great distance reduces gravity to a gentle tug, so they move leisurely in their orbits. Knowing this, scientists looked at the galaxies and measured how fast stars were moving. To their surprise, they found that while the stars closer to the center of the galaxy behaved as predicted, those further away moved far too quickly. This observation was devastating to the traditional theories of gravity and motion. If the stars were moving as fast as their measurements suggested, galaxies should have torn themselves apart. It was a crisis, and astronomers and physicists scrambled to find a mistake in their calculation. Was Newton's theory of gravity wrong? Was his theory of motion wrong? Or was it possible that astronomers had incorrectly measured the galaxy's mass? All options were investigated, and all were ruled out, except one. Today, scientists believe that the answer lies in a previously unknown kind of matter called dark matter. This dark matter can be envisioned as a cloud which surrounds most galaxies. This matter is very unusual. It is affected by gravity, but it is invisible to visible light and all other forms of electromagnetic radiation. The name dark matter originates in this form of matter's inability to emit or absorb light. Dark matter adds to the gravity of the galaxy and explains the orbital speed of stars far from the galactic center. Dark matter has not yet been directly observed, but scientists believe that it is likely to be real, mostly because the other options have been ruled out. Using dozens of approaches, astronomers and physicists continue to search for direct evidence that would prove that the dark matter hypothesis is true. This question is one of the most important physics research questions of the 21st century.
When you look at the night sky, what do you see? You see a few stars, but you mostly see dark. What is in that dark? Is it all a vacuum like we've been taught in school? What you may not realize is that the night sky really would look like this if you could see all the hidden matter that's invisible to our eyes. One of the biggest, if not the biggest question in science right now is, what is the universe made of? Sure, I've talked about the Standard Model and quantum field theory in several videos which try to explain what the universe is made of, but these so far only attempt to explain what the visible matter in the universe is made of. It turns out that visible matter, that's everything that you can see on Earth and in space with the most powerful telescopes, is only a minuscule portion of all that exists. There's about 6 times more matter in the universe than what we can see. This invisible matter is called dark matter. This means that what we're seeing are only the waves on top of the ocean. We're not really seeing the ocean itself. Yet without this ocean, we would likely not exist. So if this dark matter is invisible, how the heck do we know that it's even there? And if it exists, then what could it actually be? You'll be surprised how much we know about it. Let's look at what our best theories in science have to say about it, and that's coming up right now. It turns out that we can detect invisible matter by its effect on the visible matter that we can see and detect. The first evidence of dark matter came from Swiss astronomer Fritz Zwicky in the 1930s when he saw that the galaxies in clusters like the Coma cluster were moving at very high speed. In fact, they were moving so fast that the galaxies could not stay gravitationally bound and should have gotten ripped apart unless they had, he figured, about 100 times the matter that he could see visibly. He coined the term dark matter to describe this invisible mass. The problem was, nobody believed him. He was kind of an eccentric guy and not very likable. Most scientists either ignored him or didn't believe him. It wasn't until almost 40 years later, in the 1970s, that observations by Vera Rubin confirmed the idea of dark matter. She measured that the velocity of stars on the outer edge of galaxies was about the same as those closer to the center. But the mass at the edge of galaxies based on visible stars gets smaller. This appeared to be impossible to explain without the concept of unseen matter causing gravitational effects on the outer edges of galaxies. If you compare the orbital speed of planets around the Sun, you'll find that the speed slows down the further away from the Sun you go. The curve of speed versus distance from the Sun follows a 1 over the square root of distance relationship. However, when you look at the orbital speed of stars in the Milky Way galaxy, you find that almost all stars are orbiting at the same speed, about 200 kilometers per second. And most other galaxies seem to show the same general trend. Near the center of the galaxy, there's enough visible matter to account for the speed, but as you get further out, there's a greater and greater mismatch between the orbital speed of stars and the visible matter. This is the reason it is thought that most of the dark matter forms a kind of halo around the galaxy. There's likely less of it near the center of the galaxy, but a lot more the further out you go. Most other galaxies seem to show the same general trend. Now, how do we know that dark matter is not just ordinary matter that is hard to see, like dim stars or black holes? This was thought to be a possibility decades ago, and some of these were categorized as machos, or massive compact halo objects. But today we have so much observational data that this possibility has been all but ruled out. The distribution of dark matter based on the rotational curves gives us a clue. It appears to be distributed evenly as well as like a halo around the outer edges of galaxies and not clumped up like visible matter is. This can be explained if we theorize that this matter interacts very weakly with itself. But ordinary matter does not interact weakly and thus tends to clump together. Ordinary matter would likely not be so evenly distributed. And research as recent as 2019 from a team in Japan appears to have ruled out primordial black holes as being the source of dark matter. In addition, there are other more technical reasons having to do with the rate at which new elements were formed in the early universe, which indicate that only about 5% of the energy density of the universe can be explained by ordinary matter. The rest has to be dark matter and dark energy. I'll be getting into details of dark energy in a future video. By the way, most of the ordinary matter in galaxies is not in the form of stars and planets, but interstellar gases. If you added up all the mass of this gas, it would be about 3 times as much as the mass of all the stars and planets of the universe put together. So a pie chart of the mass of the universe looks like this: 4% stars and planets, 11% gas, and 85% dark matter. The bullet cluster is, I think, the most interesting evidence showing how the behavior of dark matter is not like ordinary matter. This is an enhanced photograph of 2 clusters of galaxies passing through each other. In a computer simulation of this, what you can clearly see is that the gases of 2 galaxies are interacting with each other and heating up to emit X-rays, which are visible as bright pink areas. This is the ordinary matter of the 2 clusters. The majority of the matter, however, as indicated by the gravitational lensing, is in the blue areas of the photo. This is the dark matter that simply did not interact with the ordinary matter or with itself as the 2 clusters collided, and thus passed right through. So you can clearly see that most of the mass is not where most of the ordinary matter is. There are some physicists who argued that dark matter doesn't really exist and that rotation curves can be explained if the laws of gravity were different at larger distances. Again, this behavior in the bullet cluster would be hard to explain if that's the case. Inventing a new particle is probably less crazy than proving the laws of gravity wrong, given the mountains of evidence that prove Einstein's general relativity is correct. So if it is not dim ordinary matter and not due to changes in gravity, then what the heck is it? Let's look at what properties a potential dark matter particle would need to have. First, it obviously must be dark. This means it does not emit any light and doesn't interact with anything to emit light or any kind of electromagnetic radiation. 2, it must, of course, interact through gravity, so it cannot be a zero rest mass particle like photons. 3, it must not interact with itself or interact very weakly with itself. 4, it must be cold. That is, it is not moving at very high speeds, because if it was, then after the Big Bang, it would have just kept on going and not slowed down to form halos around ordinary matter. And 5, it must be stable. That is, it does not decay, because if it decayed into other particles, it wouldn't still be here now in such large quantities 13.8 billion years after the Big Bang. If it's a particle, could it be hiding in plain sight in the standard model of particle physics? We need a particle that does not decay and is neutral. The only massive neutral particle in the standard model that is stable is the neutrino. But because neutrinos are so light, they're not cold. They move very fast. So they're like hot dark matter. This would preclude neutrinos from making the large structures in the universe because the neutrinos would want to move away while the ordinary matter wants to come together. So the net effect would have been a smoothing out of the ordinary matter. If we invent a new particle that does not interact with electromagnetism, has no strong force nuclear interactions, but does interact through the weak nuclear force and through gravity, then we have just invented the dark matter particle. Scientists have a name for this particle. It's WIMP, or weakly interacting massive particle. Why would this particle need to interact through the weak nuclear force? Because it turns out that if we ask the question, what is the rate of interaction of dark matter particle and antiparticle annihilation that you would need to have to give us the correct ratio of dark matter that we observe today, the answer is that they would need to interact with the strength exactly equal to the strength of the weak nuclear force. This coincidence is called the WIMP miracle. And it so happens that there is a model in particle physics that predicts exactly such a particle. This model is called supersymmetry. Scientists like the WIMP because it was not invented for the purpose of solving the dark matter problem, but comes about naturally in string theory. And string theory requires supersymmetry to work. Or maybe all this is wrong, and we need a completely new theory to explain dark matter. Either way, I think this is a really exciting area of research, and it's going to keep current and future physicists busy for a really long time.
What is the universe made of? This is a question that humans have been asking since we first looked up into the night sky. The universe is thought to consist of three types of substance: regular matter, dark matter, and dark energy. Regular matter consists of the atoms that make up stars, planets, human beings, and every other visible object in the universe.
We look in the universe and we see the effects of gravity, and let's say, let's add up all the stars and galaxies and planets and comets and black holes, everything we know about, to account for this gravity that we see. And when you add in the dark matter, this extra gravity, it turns the universe into the universe that we see. That's why we know the dark matter is real. We don't know what it is, but we know it's there because we can't make the universe as we see it unless we put this extra gravity into our simulations to match the gravity that we see.
In the last 6 decades, NASA, along with its international partners and thousands of researchers, have expanded our knowledge of the universe by using a full fleet of telescopes and satellites. They have been exploring the evolution of the universe from the Big Bang to the present.
The cosmic microwave background, a record of the earliest moments of the Big Bang. Then it takes a little time to make your first stars. We call it the dark ages. Stars are made, galaxies mature. We come up to the present day, 13.7 billion years later, and that telescope, Wilkinson Microwave Anisotropy Probe, made this measurement. And so it's a pretty coherent picture of the earliest moments of the universe.
The Wilkinson Microwave Anisotropy Probe satellite returned data that allowed astronomers to precisely assess the age of the universe to be 13.77 billion years old, and to determine that atoms make up only 4.6% of the universe, with the remainder being dark matter and dark energy. For the first 150 million years after the Big Bang, there were no galaxies or stars or planets. As time passed, the first stars formed. Stars collected into galaxies. Galaxies began to cluster together. Clumps of matter smashed into each other, and the planets in our solar system began to form around the sun. Our solar system, galaxies, and clusters of galaxies are all held together by gravity. However, something just doesn't add up. Galaxies seem to be achieving an impossible feat. They are rotating with such speed that the gravity generated by their observable matter could not possibly hold them together. They should have torn themselves apart long ago. The same is true of galaxies and clusters, which leads scientists to believe that something we cannot see is at work.
Particle physicists are convinced that it might be an exotic particle that doesn't interact with us, doesn't interact with our light or with our telescopes, but that it has gravity. So these particles are doing their own thing, invisible to us, but otherwise attracting our matter into nucleating us among them.
This mysterious substance, called dark matter, makes up the bulk of a galaxy's mass and forms the foundation of our universe's large-scale structure. Because dark matter does not emit, absorb, or reflect light, its presence is only known through its gravitational pull on visible matter in space. Another strange thing happening in the universe has been spotted by the Hubble Space Telescope. The observations of very distant supernovae showed that, a long time ago, the universe was actually expanding more slowly than it is today. However, the expansion of the universe has not been slowing due to gravity, as everyone thought. It has been accelerating. No one expected this. No one knew how to explain it, but something was causing it.
Some mysterious pressure in the vacuum of space acting opposite the force of gravity. Whatever it is, we call it dark energy. That's our placeholder term to describe what we observe. The acceleration of the universe. Nothing known will stop this.
Scientists still don't know what the correct explanation is. This energy, in whatever form, is needed to reconcile the measured geometry of space with the total amount of matter in the universe. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up about 27%. The rest, everything on Earth, everything observed with all of our instruments, all normal matter, adds up to less than 5% of the universe. The universe is far from being fully understood. There are many different theories as to what dark matter and dark energy actually are.
I have to say, again, I wrote this particular article in 2015 and it wasn't edited. I wrote it the way it came out, it just flowed out of me, and I didn't spend time editing it or revising it. I just wrote it the way it flowed out. It's a little rough around the edges, it could be reworked and edited to flow a little bit better, but that being said, the reason why I'm creating this article as a flashback video article is because these articles are fundamental in the process that I was going through to come to the conclusions and realizations that I have now come to. That is the reason why I'm taking these old articles that I wrote in 2015, 2016, and up until now, and putting them into video article format, so there is a record of them, so that they are in the catalog and archives. When I was reading a news article in 2014 talking about dark energy, and how if you throw an apple into the air hard enough, and it's able to leave the gravitational influence of Earth, it would keep moving away from Earth forever, moving faster and faster. And that really sparked my whole interest and investigation into the subjects of dark matter, dark energy, and studying the universe and how everything works. Welcome to the right side of dark energy, a universal construct. Today I want to make an introductory video to a new series of videos I am putting together to explain my theory on the universe. What is dark energy? What is matter, energy, space, and time? And what is gravity? And how do they all interact with each other? First things first, what is dark energy? Dark energy is space. Space itself is dark energy. Dark energy has also been referred to as quantum space, or quantized space, or even zero-point energy, or the universal constant. Dark energy is energy. It's not a particle, it's not a lot of things, but it is everywhere in the universe, all the way from the formation of the smallest parts of the atom, and all the way to the farthest reaches of space. What we do know is dark energy has a liquid quality to itself, but does not interact with itself, or more precisely, does not strongly interact with itself. Dark energy is almost impossible to detect. Just as looking into the vastness of empty space, it is impossible to see anything, or detect anything, or any presence of energy, but we do know it exists, and it is there, not only from the force it exerts on the universe, but also from the detection of the presence of heat in outer space. We also know dark energy exists through studies, and through quantum mechanics we have detected the dark energy field and the slight fluctuations it produces in what was thought to be the emptiness of space. So what is dark energy and where does it come from? The basic answer to that is actually quite simple. Dark energy is the entangled information of the decay of all matter in the universe. As matter decays, its energy and information decays into more space, or dark energy. Dark energy is the keeper of time and change, and all space, or dark energy, is a record of the convergence and evolution of all matter and takes the form of space. As matter decays, it creates more space, and so as all matter in the universe is decaying, it is also creating more space. That's why the universe is expanding. The decay of all matter in the universe is creating more space. Now, there are quantum states to the dark energy field, and I will not get into that here and now. I will be working on more videos to break all of this down, and I will cover the quantum states of the dark energy field and how all mass interacts with dark energy and makes up the universe. But first and foremost is to get some insight into the concept of dark energy itself before we continue. The white background represents the dark energy field. The pulsing represents the electromagnetic distortion around all matter, like two atoms. The electromagnetic distortion pushes dark energy away from matter on a gradient and makes all matter appear to have an attraction towards itself. Gravity can be defined as the electromagnetic force that matter exerts on the universe, on dark energy, that causes a dark energy field effect, or gravity. You can scale this up from atoms all the way to planets and suns and even black holes. Anything that creates gravity is actually not pulling things into itself like a gravity well. More, it is pushing dark energy away, and in doing so, dark energy is pushing harder on the side with the least distortion. As the fields touch each other, it creates a path of least resistance, and the two objects are forced together by the stronger dark energy field on the side with less distortion, giving matter an attraction towards itself. It's dark energy that causes an attraction of matter towards itself that creates gravity. With that introduction out of the way, let me go ahead and read the article. I wrote this article in early 2015 and I posted it on April 20th, 2015. The right side of dark energy, a universal construct. Dark matter versus dark energy. It could be said that there is no dark matter and there is in fact only dark energy. Dark energy is the universal constant that makes up space and is present everywhere in the universe. In parentheses, almost everywhere. Once you enter a black hole, there is something different happening. That's for another paper. End of parentheses. Dark energy has a liquid quality to itself, yet does not interact with itself. Or more accurately, dark energy does not strongly interact with itself, but it is present in the entire universe. To understand dark energy and why some have hypothesized dark matter is key to understanding the formation of the universe and why all mass, especially large clumps of mass like galactic clusters, form and behave in space. No, I am not sure what dark energy actually is. Some may call it quantized space or quantum space or even just quote-unquote space. But what is clear is how it interacts with all known matter in the universe. Let me interject right here. I'm going to say right now that particular sentence, I truly do believe that dark energy is the electromagnetic decay of all matter in the universe, and that literally creates space. And that is the reason space is expanding. The electromagnetic decay of all matter in the universe is creating more space. So, let's dive right in. In parentheses, dark energy is the keeper of time. Where there is no dark energy, there is no time. End of parentheses. Dark energy is gravity, and gravity is the dark energy field effect, where the electromagnetic energy around all matter has a repulsive effect to the dark energy field, and because of this repulsiveness, any mass that comes close to another mass seems to be attracted towards themselves because their dark energy field effect pushing all matter together.
According to current quantum theory, particles can spontaneously appear from nowhere. Apparently, they just pop into existence in the vacuum of space. Matter and antimatter, which, because they're opposites, cancel each other out in an instant.
The lifetime is 1,000 of 1 billionth of 1 billionth of a second. We are now in an ocean of particle-antiparticle pairs, permanently appearing and disappearing.
Dr. Dragan Hadjukovic thinks something else happens to these particles to produce an anti-gravity effect. For the briefest moment of their existence, these particles can be polarized, like iron filings.
The trouble is to get it in a random orientation. If there is a magnetic field, the random orientation will change. Yes.
According to Dragan, in the same way iron filings respond to a magnet, pairs of quantum particles respond to mass. With matter and antimatter, pairs are briefly orienting themselves in relation to that mass. Matter is attracted to the positive mass of a planet or a star, while antimatter is repelled by it. Dragan believes this creates a halo of anti-gravity dark energy around every mass in the universe.
All these halos together has negative pressure, what is exactly what we need in cosmological equations to produce the accelerated expansion of the universe. It means that there are both positive and negative gravitational charges. So far, we know that gravity is only attraction. It may be that gravity is also repulsion, but not between matter and matter, but between matter and antimatter.
Dark energy is gravity, and gravity is the dark energy field effect, where the electromagnetic energy around all matter has a repulsive effect to the dark energy field, and because of this repulsiveness, any mass that comes close to another mass seems to be attracted towards themselves because their dark energy field effect pushing all matter together. So, when looking at gravity, we think that gravity is the only metric to the calculation of behavior of objects in space. Atom, matter, rock, planet, star, galaxy, black hole, universe. When we apply the math to matter, the calculations break down and we see there is quote-unquote extra gravity holding galaxies and galaxy clusters together. Why is this? This is because the calculations are not taking into account dark energy correctly. And now we are back to what is dark energy. In its purest form, dark energy could be said to be the smoldering decay of all matter in the universe. All matter converts to dark energy. Matter is, quote-unquote, smoldering into more space. Active matter, like stars and galaxies, have more quote-unquote gravity than just their mass. You see, as active matter converts to dark energy, it compounds its pressure or resistance to the dark energy field, and this adds a gravitational layer on top of what can visibly be calculated as its weight. So, let us look at this in terms of not just a star, but a galaxy. On the surface, you look at the galaxy and you calculate the mass of the galaxy and you say, it doesn't add up. There needs to be something to explain why the entire galaxy is spinning at the same speed like a wheel and not like a vortex. You see, with the observable mass, you would calculate the galaxy and you would say it should not be spinning at the same speed on the outer edge as it is in relation to the inner sector. What should be happening is the inner sector should be spinning faster and it should be spinning slower at the outer edge. So there is some unknown force with an extra layer of gravity at play. And so let's call this quote-unquote dark matter. Well, this is the only reason why dark matter exists. It is a theory to explain the extra layer of gravity. You see where I'm going with this, don't you? If there is a missing layer of gravity and the decay of matter into dark energy is an extra layer of gravity, then this should all fit nicely together. Ah, I am wrong, you tell me. Am I? It's not about right or wrong. There may be dark matter, but I propose that the reason galaxies and clusters of galaxies clump, cluster, and behave like a web is because the very act of matter, quote-unquote, smoldering into dark energy. You see, when matter smolders, like let's say around a galaxy or cluster of galaxies, from matter into dark energy, there is still extreme amounts of energy associated with the freshly decayed converted dark energy. This creates a buffer zone or bubble around the galaxy and adds its own level of gravitational field or quote-unquote dark energy field. This hot bubble of dark energy around a galaxy or cluster is what some have considered to be quote-unquote dark matter. Because the energy in the newly formed dark energy has not dissipated heat and energy enough to merge with the rest of the cooler dark energy. And even though this quote-unquote new dark energy is not matter anymore and is in fact dark energy, it cannot merge with the cooler, lighter, dark energy because it is too energetic and because it is constantly being heated and renewed by the decay of the matter it surrounds. And so it has its own weight and encompasses its own zone or field and has its own gravity associated with it. These quote-unquote hot dark energy zones do merge and intertwine with other hot dark energy zones and form bridges and lattice where matter tends to converge. And at the edge of this hot dark energy bubble, it does cool and merge with the rest of dark energy as more space. And that is why the universe looks like it has large voids forming. These are giant bubbles of dark energy growing in size, being created by the conversion of matter into dark energy. I wrote that on April 20th, 2015, and in parentheses there is one more paragraph. And all of this compounds itself, and so you see space squeezing into the web of the cosmos, and it looks like matter is the soap, and dark energy or space is the bubble in the giant washing machine we call the universe. Okay, so that was the right side of dark energy, a universal construct, dark matter versus dark energy, written early 2015, and as I already said in the introduction to this video, I wrote this pretty much the way it came out, and it could use some edits. And again, reiterating, this is a flashback video article. So I wrote this particular article before I had come to the conclusions and realizations that I have now come to. That being said, it's actually very fundamental to the process of my coming to the realizations and conclusions that I have now come to, and that is why I am putting this article together as a flashback video article. Okay, so there's a couple of more points that I just wanted to add to this particular video. And again, this is just one slice of many different pieces of the whole puzzle that I am putting together. And if you watch my playlist, the Majestic Crystal Universe playlist, and you watch that from start to finish, and of course I'm adding to that playlist every day, I definitely think you're going to get a really good understanding of how the universe truly works. Now, with that said, let me go ahead and just add a little bit more information to this particular article. Space has density. Space has a liquid quality to itself, but at the same time, within the different regions of space, there are different densities of the dark energy field. So, in the deepest voids in outer space, that would be called the dark energy zone, or state 3 of the dark energy field. while within the galactic cluster, where all the electromagnetic decay of all the matter in the universe is still hot and smoldering, this is the quote-unquote dark matter state. Okay, and that would be state 4 of the dark energy field. And within the area of the stars and planets, that is state 5 of the dark energy field. And as you go into the atom, you have the 6th, 7th, 8th, and 9th states of the dark energy field. And each one of these states represents a different density of the dark energy field within those states. So the universe itself is constantly fighting and struggling. Matter and energy is constantly struggling with dark energy. And the more energy is in one area, the less dark energy is in that area. And the less energy is in one area, the more dark energy is in that area. Anyways, think of the universe and all of the galactic filaments and the bubbles of dark energy, the bubbles of absolute nothingness between the clusters of all the galaxies. Those are the dark energy voids, or the dark energy zones. In those zones, there is more dark energy and less energy, or matter. And in the areas, in the filaments where all matter of the galactic clusters and all the different stars, the galaxies, stars, and planets form within these galactic filaments, that is the energy zone. So there is less dark energy in those filaments than there is in the voids. I hope that's clear. I'm going to throw in some graphics here, and I'm also going to add some different snips and videos to illustrate this.
This computer simulation starts just 12 million years after time zero and evolves within a volume 350 million light years across. Not everything is known, including the nature of a dominant substance known as dark matter. On the left, you can see how gravity draws dark matter into filaments, like a spider's web. On the right, gas heats up as it falls into a series of deepening gravitational wells carved out by dark matter. Within the volume, tens of thousands of galaxies take shape, mainly within the filaments of dark matter. Where these filaments meet, something strange begins to happen that will affect the character of nearly every galaxy or star. Vast bubbles of hot gas begin to form and expand outward. On the left is a closer view of galaxies that are falling into one of the central regions. On the right is the gas that envelops these galaxies. As gravity draws these galaxies together, waves of hot gas explode outward. This happens when giant black holes in their centers blast inflowing matter out in ferocious winds and jets. In time, these hot bubbles push out well beyond the central galaxies. This has the effect of limiting the amount of gas that can fall into central regions, allowing smaller galaxies to form on the periphery. It also seeds the wider universe with heavier elements created in early generations of large stars. Those elements you and I are made of. This is the story of our galaxy and our world. The coming together of dark and ordinary matter. That heat up as gravity compresses them. That leads to the production of metals in stars that are spread throughout the cosmos. Finally, there is light, given off by ordinary matter in a variety of wavelengths that we can record from our tiny outpost. In a galaxy, and a universe that is dynamic and complex. on all scales of space and time.
So with all of that said, thank you very much for watching. If you have any questions, feel free to put them in the comments below. Thank you for watching and stay tuned. I will have more videos like this shortly. Thanks for watching.